Good morning, dear students. Today we're having the final 19th practical lesson at this year of advanced calculus. Actually, that's the last practical lesson of advanced calculus for you. So this lesson will be about Fourier series. This is a kind of series that approximates function on the segment of the straight line. So if power series approximates at exact point, but this trigonometric Fourier series approximates on the segment. And also this, so we will solve a task with another kind of application of Fourier series. So this is the generic form of Fourier series for 2p periodical functions. So f from x equals a0 term over 2 plus sum of an by cosine of nx plus bn sine of nx. Formulas for finding these coefficients are the following. So for a0 we integrate function f from x from minus p to p and divided by p. An found as an integral of f from x multiplied by cosine of nx and divided by 1 over p, and bn found as integral of product of f from x and sine of nx divided by p. So that's how these coefficients are found. Then, okay, let's have practice, or maybe you have some questions about theory.
Could you make attendance?
Yeah, I thought I have made it, or maybe.
You made it, but it's for yeah.
Yeah, so misclick. Okay, let me recreate it. In just a moment. I will create it for you. So now you can mark your attendance, so don't worry. Okay, more questions?
No questions.
Okay, if no questions, let's start solving exercises. So we have to expand the function that is defined on the segment minus p. So it has so it is given piecewise. So how it looks like? So this function equals to if x is less than minus, if x from what's going on? If x is greater than p and less or equals 0, so the function equals 2. And minus 1 if x from 0 to p. So this is the expression. Then this function is continued periodically. So we can see this graph here. So we won't plot it now. So we will just look at this figure. So this is the function. So graph of the function that is defined by this expression. And then what goes next? It's periodical periodical extending. So a periodical extension of this function. So we just duplicate it to the left and to the right with the period of 2p. So now I will clear all drawings, and now we'll start to calculate Fourier coefficients. So for A0, so let's calculate the integral. So 1 over p. So from minus p to p. Now I will write in generic form. And now I will split to a sum of integrals. So we'll do the following. So here, so from minus p to 0, 2 dx, and from 0 to p, minus 1 dx. I will just move coefficients out of the brackets. So now let's calculate these values. So what do we have here? So 2 by, so 0 minus p, so 2p, and minus p. And the answer will be 1. So found A0. Now let's calculate AN. So multiplying the function by cosine of nx, I will copy and paste this expression. And now let's integrate this function. So what I will receive? Yeah, so 1 over p for the first. So 2 over 2 over n sine over nx with the substitutions from minus p to 0. And minus 1 over n sine over nx with the substitutions from 0 to p. And as we can see, if we substitute 0 or p, so sine of 0, sine of pn equals 0. So all an coefficients will be equal to 0. Now let's calculate bn. So let me copy and paste it, and then correctly write down all expressions. So sine of nx dx. Okay, and now let's calculate. So 1 over p, and what I will receive minus 2 over n cosine of nx, and plus 1 over n cosine of nx. Yeah, and what about the substitutions? So from minus p to 0, and from 0 to p. Okay, and now let's calculate. So 1 over p, and yeah, let me move also n out of brackets. So we'll move n out of brackets, and what I will have, so minus 2 here, just 1 here. So so what I will have, so minus minus 2 plus stop. So minus, minus 2, yeah, plus cosine over Pn. So this expression will go away, plus 1, and so plus cosine of Pn and minus 1. Okay, let me check. Something went wrong. Yeah, I forgot I forgot 2 here, so everything is good now. So now, yeah, having the following expression, so 3 cosine of Pn minus 3. And how can we actually write down cosine of Pn? Cosine of Pn will be equal minus 1 in power of n. So if n is even, we will have we will have 1. If it's odd, we will have minus 1. So how it's written? And now let's move 3 out of brackets, and so we will receive the following. So minus 1 in power of n minus 1. And now let's simplify it a little bit. So how we will do it? So if this expression will be equal 0 if n is even. So if n equals 2k, and if it's odd, we will have minus 6 pn, minus 6 over pn. So if n equals 2k minus 1. So let me check. Yeah, signs are correct. So that's how we received value of coefficients of Bn. So now let's write down the Fourier series. We also can we'll mark a function f. So we'll mark a function s from x as a sum of this Fourier series, and it will be equal. So actually, f from x corresponds s from x. So a0 over 2, 1 over 2, and plus the following sum. So n from 1 to infinity, and this expression multiplied by sine over nx. Stop. No. Let's first of all write down like this. So we can write down like this, but we know that this expression, that Bn terms, Bn coefficients are not equal to 0 only. So when it has, when it equals, when n is odd. So we can write down like this. Let me move minus here, and I will write down like this. So 6p, and here 2n minus 1. And for sine, I will write as well. So I will replace n with 2n minus 1. So that's how we can take into consideration that terms of Fourier series are non-zero only for odd value of n. And now let's simplify it a little bit. I will move constants out of brackets, so out of the sum. So how it will look like. So that's the final answer. Yeah, not the final. We need to calculate the value of this sum of the series at discontinuity points. So actually, the function is continuous except points Pn. So 0 and plus minus Pn. So let's calculate the sum of the series at point 0. This is a jump of the function, so it will be calculated in the value of the sum will be calculated in the following way. So s from from plus 0 minus s from minus plus s from minus 0 and divided by 2. So from plus 0 2 and plus minus 1. So we will receive 1 over 2. And what about p? So actually s from minus p, s from p, they are equal. Okay, let me just substitute here. Copy and paste. So s from p plus 0, it equals 2, and p minus 0 equals minus 1. So again, 1 over 2. Any questions about this exercise?
Can you make it full screen?
Yeah, sure.
No questions.
Okay, no questions. Let's move to the next exercise. So exercise 2. We will have to expand the function f from x equals x squared. So we will continue it with period of 2p. So expand this function into Fourier series, and with the received series, we will Fourier series. We will calculate sums of numerical series. So this is the task for application of Fourier series. So the function is the following. We know that so that x square is not non-periodic, but we will continue it periodically. Let me show it one time how to plot such graphs. So x will be given from minus p to p. So that's how it looks like. So from minus p to p. And now we will move it left and right. So we will do a shift by the period of 2p. So let's shift it to the left. So x plus 2p. And I will also shift the period. So continued. To the left and to the right. So minus 2p, and here will be p, and here 3p. And we will do it infinitely. So okay, let's look at the graph that looks more beautiful. So we see that this function is continued periodically. So let's calculate Fourier coefficients. Take into consideration that function f, so this function x squared is a periodical function. So it means that coefficients bn will be always equal to 0. And for odd functions, coefficients a0 and an are 0. But in this case, bn are equal to 0. So, bn are equal to 0. And what about a0, an? Again, we'll use the formula that we used before. So x squared dx. But we can simplify this integral with taking into consideration that the function is even. So we'll multiply it by 2 and integrate from 0 to p. So it will be much more simple. So we will receive 2 over p by 1 over 2 of 1 over 3x cubed with substitutions from 0 to p. So we will receive so 2 over p by 1 over 3 p cubed. And what will be the answer? 2 over 3p square, 2p square over 3. So that's how we found a0. And what about an? Analogically, but we will multiply by cosine over nx also. How to calculate this integral? Let's remember integration by parts. So u will be equal x square, du equals 2x dx, dv equals cosine of nx dx, and v equals 1 over n sine of nx. Well, let's calculate. So first of all, some product of u and v with the substitutions from 0 to p. Yeah, just but don't lose this multiplier, 2 over p. And now calculating the following integral. So here will be 2 over n integral over so from 0 to p x sine of nx dx. So let's simplify it a little bit. So what we will receive? This product will be equal 0 because of sine of nx. So sine of pn always 0. And we will expand brackets a little bit. So what we will have? 4. So minus 4 over pn multiplied by this integral. This integral again will be calculated by parts. U equals x, du equals dx, dv equals sine of nx dx. So v equals minus 1 over n cosine of nx. Minus 4 over pn. So minus 1 over n cosine of nx multiplied by x. So uv is done. And don't forget about the substitutions. So from 0 to p and plus 1 over n integral from 0 to p cosine of nx dx. Okay, now let's start calculating this integral. So if I substitute p, I will receive the following stuff. So minus 1 over n p by cosine of pn. And if I substitute 0, I will receive 0. So we will have only this part. Then what about this integral? So 1 over n square by by sine of nx. Sine of nx with substitutions from 0 to p. So which obviously will be equal to 0. So this part is 0. And now let's calculate what is non-zero. So multiplying this part, the cosine of Pn will be replaced with minus 1 in power of n. And now let's simplify what we can simplify. So it will be equal, so actually p goes away, so we can cancel it, n square and minus 1 in power of n. So actually that's all that we received. So now let's write down the Fourier series that we have. So s from x equals f from x equals s from x, and it will be equal p square over 3 plus sum from 1 to infinity. So of such terms and cosine of nx. So received Fourier series. And we have to calculate the following series. So S1, the following numeric series. So minus 1 over n square and n minus 1 here. Actually, this is, so the module of this series is generalized harmonic series, so must be, so we will calculate it. Yeah, and this is the generalized harmonic series. So we will calculate sums of this series. So how to do it? How to receive this series from this? Stop. Oh, yeah, everything is okay, actually. But I can simplify it a little bit. So I will move 4 out of brackets. And it will look more beautiful. Okay. So S1. How to receive S1 from this Fourier series? We can easily do it with substituting 0 instead of x. So into f from x. So f from 0 equals 0, and s from 0 will be equal. So here will be 1. So how we replaced it. Then continuing transforming it. So we need to receive this series S1 instead of this series. So it will be equal. So P over P square over 3, and here will be minus 4 sums, and here I will receive n minus 1. So I divided here by 1, so and multiplied by 1, so moved minus out over the series, and it will be equal. So P square over 3 minus 4s1. So 4s1 actually will be received from the equation, from the following equation. So 4s1 equals p square over 3, and then s1 equals p square over 12. So that's how we easily calculated sum of this series. Well, how to say easily? We had to expand function into Fourier series. So calculated the first sum, and what about the second? About this sum, how to receive it? So let's calculate f from p, f from p and s from p. So f from p equals p square, and s from p, it will be equal, so using this series, so if I substitute p instead of x, I will receive minus 1 in power of n. Then so if I multiply this minus 1 in power of n by itself, I will receive minus 1 in power of 2n, and of course it will be equal 1. So we received such a generalized harmonic series that is convergent because of a power of 2. So now, and I will also substitute this series with S2. So what next? Again, we will solve equation with respect to S2. So it will be equal P square. Then 4s square will be equal 2p square over 2 over 3. And then S2 will be equal p square over 6. So that's the sum of the numerical series that we received. Any questions about this exercise?
No.
Okay, if no questions, let's have a break for 5 minutes, and after that we will continue expanding function into Fourier series. Let's continue. So now doing the next exercise. So task 3 is the following. We will have to expand the following function. F from x equals p minus x. And we'll expand it into Fourier series in 2 ways. So in terms of cosines and in terms of sines. So what does it mean actually? So if we expand in terms of cosines, it means that we will continue function f from x in the even way. And it will look like this. So we have the condition that the function is defined on segment 0b. Sorry. So we will define sorry. We will define it in even way. So this is the initial function. This is the so we continued it in even way and then continued it periodically with period of 2p. So that's how it looks on the graph. And how Fourier coefficient, so how Fourier coefficients will look like. Bn will be equal to 0. And A0 will be calculated as 2 over p integral from minus p to p from 0 to p f from x dx. So p minus x integrated from 0 to p. So it will be equal. So px minus 1 over 2x square with substitutions from 0 to p. Okay, let me extend it. Well, make it full screen. So it will be equal. So 2 over p and multiplied by p square over 2. So, and it will be equal p. So found A0. And what about AN? So multiplying our function by cosine of nx. And then we will integrate it by parts. So u equals p minus x. Du equals minus dx. dv equals cosine of nx dx. And v equals 1 over n sine of nx. And now substituting everything. So uv, first of all, with the substitutions from 0 to p. And yeah, so du equals minus dx, so plus 1 over n integral from 0 to p sine of nx dx. And now let's simplify it. So this expression will be equal 0. So I will just do like this. So I will receive the following expression: minus 2 over p n square cosine of nx, with substitutions from 0 to p. So what we will have, so minus 2 over pn square, so, and in brackets, minus 1 in power of n, minus 1. And I also will change the sign as well. So here will be 1 minus 1 in power of n. And how to simplify it? So if n is even, this expression equals 0. So if n equals to k. And if n is odd, it equals 4 over pn square. So how we will write the sum of so the Fourier series and the sum of Fourier series? So in the following way. So as this function is everywhere continuous, so we will so s from x will match f from x. So p over 2 plus so sum from n to infinity, and here I will substitute 2n minus 1 square and cosine over cosine of 2n minus 1x. Moving constants out of the sum, and we will receive the following series. So done with part A. So this is the Fourier expansion in the form of cosines. Any questions about this exercise? So in terms of cosines, yeah.
No.
Okay, if no questions, let's move next. Part B. So we will have to expand. So we'll expand the function into Fourier series in terms of signs. So we will continue this function periodically in odd way. So this is our initial function, and if we continue in an odd way, we receive this part at the left, and then we continue this function periodically on the whole numerical axis with period of 2p. Now we will have to calculate only bn, because a0 and an will be equal to 0 in this case, if the function is odd. So bn will be calculated by the following formula. So 2 over p, integral from 0 to p. with from 0 to p, because we continue into we already took everything into consideration, so it will be enough. So then, what we will do next, we will calculate the integral. So p minus x by sine of nx from 0 to p. We will integrate it by parts as well. U equals p minus x. Du equals minus dx. Dv equals sine of nx dx. And dv equals minus 1 over n cosine of nx. So now integrating it. So uv first of all. And with the substitutions from 0 to p. And minus here, and minus before the integral will be because of it. So from 0 to p, 1 over n cosine of nx dx. Okay, now let's calculate these parts. So what do we have here? So if I substitute p, I receive 0. If I substitute 0, I will receive p. Yeah, by the way, let's first of all move n out of brackets. It will be easier. Much easier. And after that, we will calculate. So if I substitute here p, I will receive 0. If I substitute 0, I receive p, and p will be subtracted, so it will be equal p. And what about this integral? It will be equal 1 over n sine of nx with the substitutions from 0 to p. And this integral will be equal p. So this part will be equal 0. So the answer will be 2 over n. So this is the coefficients Bn are the following. And now let's write down the sum of the series. So s from x equals, so n from 1 to infinity, 2 over n sine of nx. So that's the Fourier expansion for this function in terms of in terms of signs. And it is always continuous except points Pn. So let's calculate it at point 0. So s from 0 will be equal f from plus 0 plus f from minus 0 over 2. So f from plus 0 equals p. F from minus 0 equals minus p. So over 2, and the answer will be P. Yeah, actually, in other discontinuity points, it has the same value. So that's all for this exercise. Any questions? Okay, if no questions, let's move to exercise 4. So we have the following function. It is given graphically, and we'll expand it into Fourier series. But first of all, let's write down the analytical expression for this function. So we can see that it has period of, so it is repeated on the following periods. So from -2 to 2, from 2 to 6, so it has period 2L, so period is t equals 2L equals 4. So this is the period of this function. And how to write down the analytical expression for this function. So let's start from an easier part. So it equals 2 when x is from 0 to 2. And what about this expression? So we can see that angle coefficient is 1 over 2. So 1 over 2x, and shift to the upper side is 1. So 1 over 2x plus 1. If x is from -2 to 0. So this is the expression. So this function has period of 2L. Let me clear my drawings. So these are formulas for Fourier series for 2L periodical functions. They look similar to series for 2P periodical functions, but here L equals P. So that's why it is cancelled. So the general form is, so argument of the sine and cosine looks like this. So P n x over L. And when calculating coefficients, we replace P with the L. So actually that's the difference. So now let's calculate Fourier coefficients for this function. So A0 equals 1 over 2 integral from -2 to 2 f from x dx. So it will be equal. So 1 over 2 and okay, let me duplicate and then I will fix it. So 1 over 2x minus 1 here, and 2 in this integral. So let's calculate. So 1 over 2 and then 1 over 4x square plus x with the substitutions from -2 to 0 plus 2x with the substitutions from 0 to 2. So 1 over 2. So if I substitute here 0, I will receive 0. And what about -2? So -1 plus 2, and stop, -1, yeah, plus 2, and plus 4. So 5/2. So everything is okay, correct. So now calculating an. Multiplying it this function by cosine. P n x over 2. And here I will substitute this p n x, this cosine. So let's calculate, let's calculate this integral by parts. So u will be equal 1/2x plus 1. Okay, I can remove brackets. Du equals 1/2 dx. dv equals cosine of pnx over 2 dx. And v equals 2/pn, sine of this value. So now let's start substituting. So don't forget this 1/2 multiplier. So this expression with substitution from -2 to 0 plus, stop, not plus, but minus -1/pn, because, yeah, so 1/2, so cancel them. Integral from -2 to 0, sine of pnx over 2 dx. And then plus 1/pn, sine of pnx over 2, with the substitutions from 2 to 0. Let me double check it. So here sine, here correct, sine here. Okay, and now let's look what can we simplify. So this part is cancelled, and this eliminated as well. So the expression is simplified a lot. So we will have 1/2 pn minus 1/2 pn, and the sine of this expression. Minus 1/2 pn integral. So let's integrate it. We will have minus will be eliminated, 2 will be eliminated, and I will receive 1/p square n square cosine of pnx over 2. With the substitutions from -2 to 0. Okay, just a moment. I will go away for 2 minutes. Yeah, let's continue. So calculating this integral, so it will be actually equal, so minus 1, so 1 minus 1 minus minus 1 in power of n. And let's try to simplify it. So if it equals 0 if n is even, and it equals 2 over p square n square. So if n is odd. Okay, let me check my notes if it matches, because a lot of calculations. Yeah, so it matches. Good. Now calculating Bn. Okay, let me just copy and paste it and replace cosine with sine instead. So the following stuff. Okay, so u equals this expression and du equals 1 over 2 dx. Then, yeah, so this integral as well will be calculated by parts. So dv equals sine of pnx over 2 dx, and v equals minus 2 over p over pn cosine over pnx over 2. So now let's calculate it. 1 over 2. So calculating uv with the substitutions from minus 2 to 0. Plus 1 over pn integral from minus 2 to 0 cosine of pnx over 2 dx. So done with this first integral, and what about the second one? Minus 2 so minus 1 over pn cosine of pnx over 2 with substitutions from 0 to 2. So now let's simplify this expression a little bit. So let's move 1 over pn out of brackets. It will be easier a little bit. Then, what next we can simplify? If I substitute 0, what I will receive? So minus 2 multiplied by what's going on? So minus 2 multiplied by minus 1 in power of n. And if I substitute minus 2, I will receive 0. So just this part remains. then plus 2 over Pn sine over Pnx over 2 with the substitutions from -2 to 0. And it will obviously equal 0. And minus, so substituting 2 will receive cosine of Pn. So -1 in power of n -1. And now let's simplify it a little bit, yeah, but let we not lose this multiplier. So -2 multiplied by -1 in power of n minus -1 multiplied by -1 in power of n and plus 1. So the final answer is 1 minus 3 multiplied by -1 in power of n over 2 Pn. Let me check with my notes. Y2. Weird a little bit. Okay, let me check what went wrong. Y2 instead of 3. Because yeah, it must be must work in an so in another form. So why it behaves in such way? So Bn started so the following integral. So here minus -2 over Pn cosine of this expression. Yeah. Oh, well, that's weird. And, well, I guess that some mistakes in my notes.
Is it possible that mistake is higher than finding Bn?
Where? Yeah. So in AN, you mean?
Yeah. Yes.
No, it's correct. So everything matches. So AN and BN don't depend on each other. Absolutely. Well, it seems that yeah, something is wrong in my notes. So it must be here minus. So here must be 3 instead of 2. So that's a mistake in notes. Okay. Yeah. I will correct it in another way. So we'll draw here. So 3 here. Okay. Yeah, and also need to recalculate all this expression. Okay. So let's return here. So what we received? What we actually received? So all Fourier coefficients. So we can write down the sum of the Fourier series. So coefficient A0 equals 5 over 2, and A0 over 2 equals 5 over 4. Then so writing down the sum. So as for Bn no specific behavior for even or odd n, so it means that so we will write down an like this. So without simplifying it, and it will be multiplied by cosine over p n x over 2. Okay, let me move it into the numerator. And what about n? Or what about bn? It will be equal the following stuff. Plus this expression multiplied by sine of pnx over 2. Well, what can be also simplified? We can move 1 over pn out of brackets. And that's all. What can we simplify? Okay, and also what about discontinuity points for this function? So s at point 0 will be equal f from 0, from plus 0, plus f from minus 0 over 2. So f from plus 0 equals 2. F from minus 0 equals 1. So 3 over 2. And what about points minus 2, 2? So it will be equal. S from 2 plus 0 plus S from 2 minus 0 over 2. So S from F, not S, but F. So F from 2 plus 0 equals 0. And F from 2 minus 0 equals 2. So it equals 1. So found it. Any questions about this exercise?
No.
About the whole lesson, about previous lessons, maybe some organizational questions?
No questions.
Okay.
For now.
So it seems that our meetings finished this year. So it was a pleasure to work with you. So I wish you good luck on your session. Send your individual tasks, submit your individual tasks who haven't done them yet. So I wish you good luck. Stay safe, and thank you for your attention.
Thank you very much.
Thank you
Thanks
very
for the
much.
lesson.
Goodbye.
Bye.
Goodbye.
Thanks for the
Goodbye.
lesson. Also, good luck.
Thank you.
Bye.